Hi, everyone. I'm Jamie Peterson, Director of WolframU. 4 weeks ago, we launched version 15 of Wolfram Language and Mathematica, and today we continue with our new in version 15 webinar series. Today's session is dedicated to what's new in mathematical functionality, including applications of non-commutative algebra, special functions for quantum field theory, neural networks and symbolic differential equations, and recent advances in PDE modeling. Joining us today to deliver talks in their areas of expertise are members of our mathematical computation R&D team. Devendra Kapadia, Adam Strabansky, Jayanta Padakar, Tigran Ishkanyan, Aram Manasalian, Syria Sededin, and Oliver Rubin Koenig. You'll want to take a look at Stephen Wolfram's release announcement for his comprehensive coverage of new version 15 functionality and his philosophy for using Wolfram Language and applying computation in the world of AI. The blog has several sections that relate to the mathematical functionality you'll be seeing today. To try examples from today's presentation, you'll want to access version 15, and we have a free trial offer so you can get started right away. I'm going to ask a poll question to the webinar audience now about whether you've already upgraded to version 15. We have a YouTube live stream audience as well, and for those of you on YouTube, please feel free to type your responses, comments, and questions in the chat. We have Wolfram webinar and technical staff joining during the live stream to help us coordinate Q&A, so I encourage you to type your questions as we go along. Our staff will answer what we can in typed responses to you, and our presenters will have a few minutes at the very end to address remaining questions. So let's take a look at the poll question. Very nice. So many, the good majority of you have already upgraded to version 15, and that's great because you'll have access to all the latest functionality. Let me point out just a couple things in the webinar interface before I go. The chat and Q&A area is on the right of the screen, and that's where you can submit questions as we go along and where you can read the published Q&A. A download link with the webinar notebooks appear as a pinned note at the top of that chat panel. And then finally, make a note of the full screen toggle that's available in the top right corner of the presentation window in case you want to make that area larger. We've been making new notebooks available each week as we continue the series, and we hope that you'll join us at the final session, which will take place next Thursday. Thank you for your attention. We have lots of important talks to get to today, so without any further delay, I'll pass things over to Devendra, who will provide an overview of the latest math functionality.
Thank you, Jamie, and welcome everyone to this wonderful new session on what's new in mathematical computation version 15. And I decided that we should call it mathematical computation for the age of quantum and AI. So when I was a student, quantum theory was something very esoteric. A handful of people knew it. But today, quantum computation has gone to the masses with all the talk of building quantum computers. It's even on the stock exchange, so that's great. And then you've got AI, the LLMs, which have been the center of so much attention. So what I'd like to do is to begin today's webinar by giving a brief idea of how we think we fit into that whole picture of quantum and AI. So we have 4 talks today, and the first talk relates to non-commutative algebra. So we introduced non-commutative algebra in version 14.3, and the idea is very simple. You've got 2 things, P and Q. Think of them as variables, operators, whatever you like, and P times Q is not equal to Q times P. That's non-commutative, right? And so that was a big advance. But the question we didn't completely ask ourselves was, if PQ is not equal to QP, then what is it equal to? And that's the question we answer in version 15.0, where it turns out that as long as PQ minus QP is sufficiently simple, one can have a nice theory of non-commutative algebra. And so you see over here, this so-called commutative bracket, PQ minus QP equal to 1. That's something related to what's called a Weil algebra, which was introduced by Hermann Weil, the great mathematician Hermann Weil, in trying to explain quantum mechanics in the 1920s in So in that era. But we have a lot more than that. We got Weil algebras, Grassmann algebras, Clifford algebras. And to present that to you, we have Adam Strasbonsky, who will give a very rigorous, complete account of what's been achieved over here. Like everything that Adam does, it'll be very complete, very powerful, very usable. And I think that's a talk that's well worth listening to. The second presentation for today is about quantum field theory. See, so quantum mechanics was a 1920s and 1930s product, but then it was mostly about particles and things like electrons, etc. So people started asking a question: what about fields? What about the electromagnetic field? The Maxwell equations, can one quantize them? And that turned out to be a much harder problem than people had thought. In fact, Paul Dirac, the great physicist, almost gave up working on it, and then came along a bunch of young physicists, Feynman, Tomonaga, and Springer, who cracked this problem of quantum electrodynamics, or QED, and they received a Nobel Prize for it. And of course, that is a beautiful piece of work, but what has survived from that theory is something called a Feynman diagram. So Feynman diagrams were introduced by Richard Feynman in trying to explain these very complicated calculations. And if you do a Feynman diagram calculation, eventually need to do a Feynman integral calculation, which is what you see over here. So these are multivariate, in some sense, integrals over what's called momentum space. And to evaluate them, you need special functions, new special functions, multiple zeta, multiple polylog, multiple harmonic number. And that's the theme for today's second talk by Jayant Fadikar, speaking on behalf of himself and Tigran Ishkanyan. This is very beautiful modern stuff, thoroughly state of the art. I should warn you that the first two talks for today are technical, but for that very reason, they are worth listening to. This is deep work. They have spent quite more than a year thinking deeply about it. It's hard to convey these things in 20 minutes, but they'll do their best, and I hope you will enjoy the session. So that's about the quantum aspect. Now I slowly move towards AI. So here you see, what you see over this beautiful plot with a 3D plot. It's a complex plot actually. Is the plot of the solution of a first order differential equation. And it looks like just any other solution plot. But if you were to go close enough to the plot and the solution, ask it, where do you come from? It will tell you, I come from a neural network. So this solution was derived using a neural network in DSolve, the differential equation solver for version 15. That's a team effort by a neural networks and symbolics team working together to produce this, I think, nice breakthrough, which tells us that, yes, big is powerful, the LLMs are powerful, but small is beautiful too. And our small little neural network, homegrown network, is hallucination free. It fits marvelously in DSolve and behaves just like any other solver inside Mathematica. To present that to you, we have Aram Manasalian, the developer for DSolve, and Sira Saduddin from machine learning team. So Aram and Sira will tell you the story behind this neural network for solving differential equations. So that's three talks, and the fourth talk is relates to actually what is really a big area, the PD modeling world, the world of finite elements. And over here we have some very beautiful advances, and to talk to you about them, we have Oliver Rubin-Conning, who manages that part of the team. So his team have come up with some very nice breakthroughs. So here is in fact, the eigenfunction plot in the spirit of quantum things today in polar coordinates. So one wants to switch different coordinate systems, and version 15 lets you do that. There's some nice plasticity improvements, some fluid flow, swirl flow improvements. There is a beautiful monograph about what's called a Schrödinger-Newton equation, which I regard as an excellent attempt to understand quantum gravity. First attempt. Sometimes the smallest advances lead to the biggest ideas. So Oliver is just so deep into all that. And the reason why his talk is last is because I think Oliver is also a wonderful presenter. So I think you'll really enjoy that talk. I urge you to stay to the end and listen to Oliver talk about the PD modeling world and recent advances. So we have these 4 talks. In the interest of time, we'll just keep going through them one by one. But then at the end of it all, you'll have a chance to ask us questions in person if we have some time. But along the way, please feel free to ask questions in the chat, make comments. I learn a lot from them. Some of my own misconceptions get cleared up that way. So you learn, we learn. You're here. You've taken the time to come here. We appreciate that. And I promise you, if you ask a question, we'll try and answer it as honestly and completely as possible, either during the webinar or at the end of it. So it's a great pleasure to have you all here. And as usual, a very great pleasure to have the WolframU team backing us up, Robs Martinez and Jamie Peterson, who are always so helpful to us. So with their support, we'll now launch into these 4 talks, and I hope that you'll enjoy them. I hope you will let us know how you feel about the new release, what you'd like to see in future. And with those words, I'm going to hand over and let the webinar begin.
Hello, my name is Adam Strzeboński, and today I will be talking about non-commutative algebra and its applications. So, non-commutative algebra functionality has been introduced in Mathematica 14.3 and has been significantly extended in Mathematica 15. So let me discuss the non-commutative polynomial functions that we have. So in Mathematica 14.3 for algebra representation, we had non-commutative algebra objects. And in Mathematica 15, we additionally have Weyl algebra, Clifford algebra, and Grassmann algebra. So for dealing with non-commutative polynomials, we have non-commutative polynomial Q and non-commutative variables. We have polynomial transformations, non-commutative expand, and non-commutative collect. We have Grobner basis related functions, non-commutative Grobner basis, non-commutative polynomial reduce, non-commutative polynomial reduction, which is a new function in version 15.0, and we have non-commutative monomial list. And also related functions are generalized power, commutator, and anti-commutator. So first, algebra representation. A non-commutative algebra object represents a unitary algebra. It is used in non-commutative polynomial functions to specify the names for algebra operations, neutral elements of addition and multiplication, variables that are assumed to represent scalars, and variables that are assumed to represent commutative elements of the algebra. An algebra is a vector space equipped with a bilinear product operation. An algebra is unitary if its product operation has a neutral element. In Mathematica 14.3, non-commutative algebra objects represents always 3 algebras. So algebra elements are non-commutative polynomials in symbolic variables, and the variables do not satisfy any relations. That is, distinct expanded polynomials represent distinct algebra elements. In Mathematica 15.0, it is possible to specify algebra generators and relations that the generators satisfy. In this way, we can represent arbitrary, finitely generated unitary algebras. So this gives an algebra with default settings. It's represented by a non-commutative algebra object. We can see the multiplication, addition, unity, and 0 in this format. There are also other properties of the non-commutative algebra object. Here is the full listing of them. So the algebra underlying expression contains definition of multiplication, addition, unity, 0, commutative variables, scalar variables, generators, relations, commutation relations, structure, specification, variable order, and word order. So here is how to extract the property values. We just say algebra of the property name, and for instance, this gives the unity. So something that's new in version 15.0 is algebras given by generators and relations. So let us specify an algebra with generators x and y. satisfying relation y squared equals x. So here it is. We define non-commutative algebra like this. And now non-commutative expand automatically uses the relations to put the result in canonical form. So we expand fifth power of 2x plus 3y. And as you can see, power of y higher than 1 have been replaced by x using this relation. So we only have polynomials that are linear, at most linear in y. And the canonical form is obtained by reducing the polynomial modulo, the Grosvenor basis of the relations. So the non-commutative algebra object automatically computes the Grosvenor basis, and thus the non-commutative expand uses is to reduce the polynomials. So let's talk about monomial ordering. So a list of lists of variables together with the variable order and word order specified in the algebra determines a multi-graded monomial order. Here are the default settings of the variable order and word order. So variable order is increasing and the word order is lexicographic. So monomials are ordered first on the number of occurrences of the variables from variable list VSI, starting with the list that contains the largest variables, then on the number of occurrences of commutative variables. If all the number of occurrences are the same, monomials are ordered using the word order. Non-list element of the variable list are equivalent to one element list, so pair of xy is equivalent to pair of singleton x singleton y. And we have non-commutative monomial list function that gives monomials of the given polynomial in the specified monomial order, starting with the largest. So let's define a polynomial. And now let's look at monomials in the decreasing order. So this is for the order determined by xy. And this is the order determined by pair of xy. As you can see here, anything that contains y is greater than something that doesn't contain y. And here the polynomials will be first order on the total degree in x and y. And then y is greater than x. So as you can see here, x squared is greater than 6y, and here 6y is greater than x squared. So let's talk about algebra with commutation relations. These are a special class of algebras. So when commutation relations are given, all algebra elements can be uniquely represented as linear combinations of canonical monomials in this format. So powers of all variables, which means that we can reorder all variables to get this format. So the polynomials look like commutative polynomials, except that commutation of variables may add some terms. So the commutation relations need to have the form xj times xi minus cij, xi minus xj minus dij. So if we commute variables xj and xi, we have to multiply the commuted variables by some non-zero scalar, and we have to add a polynomial. So the polynomial has to be smaller in the monomial order, has to have all monomials smaller in the monomial order than xi, xj. And also there need to be some conditions satisfied by the commutation relations, by the dij and cij here. And those conditions are chosen so that they guarantee that the commutation relations form a Grosvenor basis. And so this is a bit technical, but all our built-in special algebras actually have commutation relations. So here's how to construct one manually. So construct an algebra with commutation relations. We start with generators x, y, z, and the relation that looks like yx is equal to xy plus x, and similar relations for other variables. And non-commutative expand will automatically use the commutation relations to put the result in the canonical form. So as you can see, the variables have been reordered, but also this generated additional terms. And as I have mentioned, all built-in special algebra have commutation relations specified. So let us talk about special algebras. So this defines Weyl algebra A2. The algebra has automatically defined commutation relations. So for instance, this puts the algebra and element in the canonical form. So the canonical form will put the xy variables before the derivative dx and dy variables. But reordering introduces additional terms. So this defines a Clifford algebra, CL02. And the algebra has automatically defined commutation relations, and this particular algebra is isomorphic to quaternions. So each element has 4 coordinates that correspond to quaternion coordinates. So this is the constant coefficient, the coefficient at E1, E2, and the coefficient at E1 times E2. As you guys see, the 5th power reduced to this polynomial that doesn't contain anything beyond the product of E1, E2, doesn't contain higher powers. So let's show an application of algebra with relations. So we can show that the Woodbury matrix identity, so here's the identity, is true in an arbitrary algebra and requires only the minus 1st power to be in inverse. So it actually doesn't have anything, that doesn't require the objects to be matrices. It's just true with every algebra with an inverse. So how do we prove it? We first convert the formula to use the default multiplication and the symbolic inverse represented by inv. Now let's find all the inverses in this formula. So now the generators of the algebra that we will construct are the variables a, c, u, v, and the inverses that were present in the formula. So these are the generators. Now we list the relations implied by the definition of the inverse. So we use the inverse is two-sided inverse, so we got 2 relations for each of the inverses. This is the list of relations. Now we defined an algebra given by our generators and relations. We got 2 relations for each of the inverses. This is the list of relations. Now we defined an algebra given by our generators and relations. And now we can see that the difference of the side of the identity is 0 in this algebra. So we just use non-commutative expand and we got 0. And we have proven the identity for arbitrary algebra with an inverse. And for the second application, this is application of left Grobner basis in Weyl algebra. and to solve an overdetermined system of homogeneous linear PDEs with polynomial coefficients. So let us define the equation, convert them to Weyl algebra elements. So these are the rules for converting equations to algebra elements, and here's what we get. So we replace the derivative with the symbolic dx dy elements. We compute the left Grosvenor basis of the ideal generated by the Weyl algebra elements. And well, the Grosvenor basis generates the same left ideals, meaning the same, it will have the same, if we interpret those elements of Weyl algebra as differential operators, it will have the same solutions as the original equations. So now these are rules for converting Weyl algebra elements to differential equations. So let us now convert the Grosvenor basis to differential equations. As you can see, we get only two equations, and they are much simpler than the one we started with. And those pair of equations can actually be solved with dissolve. And we get the solution. And we can check that the solution satisfies the original equations. And this was the last example. Thank you for listening.
Hello everyone, my name is Jayanta Fadikar and I'll be presenting on special functions for quantum field theory. So in Wolfram Language version 15, we're adding some new special function capabilities. The first one is that we're adding a third argument of harmonic number, so that becomes decorated harmonic number. And then we're adding 7 new special functions, starting from alternating harmonic number, which is the alternating version of the harmonic number. Then we have hyperharmonic number, which is the cumulative version of harmonic number. Then we have multiple harmonic number, which is the multiple version of harmonic number. Then on zeta and polylog side, we have multiple zeta, which is the multiple version of zeta. Then we have multiple polylog, which is the multiple version of polylog. So multiple polylog is the extension of some definition of polylog. And we have harmonic polylog and generalized polylog, which are the extensions of integral definition of polylog. So why we are interested in these functions? The main application area is Feynman integrals. So they naturally generate iterated sums and iterated integrals, and these can often be expressed in terms of these special functions. Let us start with the new harmonic numbers. As you may know, we already had this 1 and 2 arguments forms of harmonic number n and harmonic number n comma r. So in version 15 we have introduced harmonic number n comma r comma s. I'll explain what this s means. In parallel, we are also introducing alternating harmonic number n, alternating harmonic number n comma r, alternating harmonic number n comma r comma s. And similarly, we have hyperharmonic number. Here, the label p is different from the harmonic number and alternating harmonic number, but the rest of the arguments, as you can see, they follow similar pattern. Similarly, we have multiple harmonic number n, multiple harmonic number n comma a list of weights, then multiple harmonic number n comma a list of weights and a list of color values. So let us see what these arguments mean in details. So here is the definition of the ordinary harmonic number. We sum basically from 1, then half, and 1/3, and so on. And this is the generalized harmonic number. So there is a power form in the denominator, and this exponent r comes as the second argument. And we can verify this using our function sum. So in the three arguments form of harmonic number, this s is called the color or decoration value or numerator weight, and it comes here in the numerator in this power form. And we can verify this using the function sum. So the three argument form of harmonic number, it is a representation of the truncated polylog. So if we take n to infinity here in harmonic number, we get polylog. And we can evaluate it numerically for finite n. Alternating harmonic number, as we discussed, it is the alternating version of the harmonic number. So this is the one argument form, the two arguments form, and the three arguments form. And you can see from here how it mirrors harmonic number, just that we have alternating signs here. We can verify this again using the function sum. We can evaluate this numerically, and so on. Let us now look at hyperharmonic number. This is the cumulative version of harmonic number. So when the level or p is set to 1, then we get back harmonic number. And we get higher levels of hyperharmonic number by summing the lower level hyperharmonic numbers. For example, if we sum up hyperharmonic number 1, n from n equal to 1 to k, we get hyperharmonic number 2, k. If we sum up hyperharmonic number p, n, where p is a positive integer, from n from 1 to k, we get hyperharmonic number p plus 1, k. And we can check these identities using sum and so on. And we can extend these identities for the three argument form and for the four arguments form as well. We can evaluate hyperharmonic numbers numerically in this way. Now let us look at multiple harmonic number. So multiple harmonic numbers are represented by nested triangular sums, something like this. So recall, this is the definition of harmonic number. We have 1 over I1 squared, say, I1 going from 1 to n. In multiple harmonic number, we will have two indices in the sum. So I2 will go from 1 to I1 minus 1, and I1 will go from 1 to n. And these exponents 2 and 3, they come over here. And similarly, we can have the three argument form of multiple harmonic number. So recall, this is the three argument form of harmonic number. So this numerator weight, this one comes here as the third argument. And in multiple harmonic number, we have more than one of such numerator weights, and they come over here in a list in the third argument. We can evaluate multiple harmonic number numerically in this way. Now let us look at the new zetas and polylogs. So we have the Riemann zeta function, which is defined by a series like this. And if we extend it to multiple indices, similar to what we do for multiple harmonic number, we get multiple zeta. So as you can see, the index I4, that goes from 1 to I3 minus 1, I3 goes from 1 to I2 minus 1, and so on. And these exponents 4, 2, 8, 3, and so on, they come here in the argument in a list. So for simple enough parameters, multiple zeta will auto-evaluate in terms of simpler functions. But if these are more complex, it may not auto-evaluate, but we can always numerically evaluate such functions using the function n. It is worth noting that multiple zeta is actually the limiting value of multiple harmonic number at n equal to infinity. So if we let n go to infinity, we recover multiple zeta. Now let us look at multiple polylog. So we have the series definition of polylog here, and if we extend it to multiple indices, we get multiple polylog. Note that these exponents from the denominator come here in the first argument, and these weights from the numerator come to the second argument in a list. Multiple polylog will also evaluate in terms of simpler functions when these parameters are simple enough, but in other cases, when it doesn't evaluate in terms of simpler functions, we can always evaluate this thing numerically using the function n. Similar to multiple zeta, multiple polylog is the limiting value of the decorated multiple harmonic number, or the colored multiple harmonic number, or the three arguments form of the multiple harmonic number. So if we let this n go to infinity, we recover multiple polylog. Now let us look at harmonic polylog and generalized polylog. So as we saw, multiple polylog is the extension of the series definition of polylog, and harmonic polylog and generalized polylog, they are the extension of the integral definition of the polylog. So let us look at the integral definition of polylog. So here is the integral definition of log. It is simple enough. In polylog, in the denominator, we have the roots at 0 and 1 of these forms. And these integrals are known as iterated integrals. So basically the variable x3 that goes from 0 to x2, x2 goes from 0 to x1, and x1 goes from 0 to some upper limit, which becomes the second argument of polylog. And this 3 basically corresponds to the number of factors over here. And similarly, polylog n comma k, that would be something like x1, x2, x3, x4, and so on. So n minus 1 zeros, and then followed by one form of this type. So basically this has the root 1 and everything else has the root 0. And this is the 3 argument form of polylog. This is also called Nielsen polylog. So basically here similarly we have roots 0, and then the roots 1 will repeat a few times. So n1 comma n2 comma k means that we have n1 zeros followed by n2 ones, and the upper limit of the integral that comes as the third argument. So as you can see, both in polylog and Nielsen polylog, the roots are always 0 and 1, and there is a specific order in which they are arranged. So first we have all zeros and then we have all ones. So in harmonic polylog, what happens is that the roots can be -1, 0, or 1, and they can be arranged in arbitrary order. So for example, here we have the root at 0, then -1, then 1, then 0, then 1, and so on. And those roots come in the first argument of harmonic polylog in this way. And this one, what you are seeing here, is a concatenated version of this harmonic polylog over here. Okay. Now in generalized polylog, which is also known as Goncharov polylog, we permit arbitrary complex letters as the roots. So here the roots are no longer limited to -1, 0 or 1. They can be arbitrary complex numbers. And the roots come over here in the first argument of generalized polylog. So this is the hierarchy here. We have log, then polylog. The 2 arguments form a polylog, then 3 arguments form a polylog, then harmonic polylog, then generalized polylog. Now both harmonic polylog and generalized polylog will auto-evaluate in terms of simpler functions when the parameters are simple enough. But even if they don't decompose into simpler functions, we can always evaluate those numerically using the function n. Okay, now let us go to some applications. So we will look at the applications in quantum field theory. So let us look at how these functions arise when we try to analyze particle interactions. So you may know that in quantum field theory, we do not generally predict one exact outcome of a particle interaction process. Instead, we predict a probability distribution of the outcome. So let us say there are some incoming particles and the process happens and we get some outgoing particles. Now to predict different aspects of the outgoing particles, like what types of particle come out or what are their velocity, momenta, energies, and so on, we use the so-called Feynman integrals. And there are different methods for solving Feynman integrals. The 2 popular methods are the differential equations method and the Mellin-Barnes method. And in the differential equations method, what we finally have to solve are the so-called iterated integrals. And in Mellin-Barnes method, what we have to solve finally are the iterated sums. And it turns out that many such iterated integrals and sums can be written in terms of these special functions: multiple zeta, harmonic polylog, generalized polylog, and so on. So here are some more details. As I was telling that here we want to predict the probability distribution of the possible outgoing particles and their momenta, energies, directions, and so on. And these quantities, of course, depend on the input physical data of the process. That means the masses, momenta, energies, spins of the particles involved. Now, the computation of the output, the probability distribution of the output, that goes through a chain of mathematical reductions, and the central objects there are Feynman integrals. So there is not one Feynman integral. The final step comes from the contribution of many individual Feynman integral contributions. Now, as I was telling that often the solutions can be expressed in terms of multiple zeta, harmonic polylog, and generalized polylog. And these are the 2 important methods. So in differential equations method, we get a system of differential equations like this. So those are so basically that is a system of ordinary differential equations. And there is a perturbation parameter over here. So that means we have to solve this perturbatively using asymptotic desolve. And here is one such example. So we are solving up to order 3. And as you can see, we get solutions in terms of harmonic polylog. And the second example is from a popular package known as Fuchsia. So here also we can solve it. So this is our the system of differential equations in vector notation, and we get the solution in terms of harmonic polylog. Now in Mellin-Barnes method, what we do is that we convert the Feynman integral to a Mellin-Barnes integral, and then we find the solution by summing up the residues. And when we try to sum up the residues, we get what is known as harmonic sum or Euler sum. So in its most general form, it has this form. So n to the power of p, m to the power of n into integer powers of certain harmonic numbers. And these harmonic numbers can be harmonic number, alternating harmonic number, hyperharmonic number, multiple harmonic number, and so on. So here are some examples. These are some finite Euler sums. For example, this goes from n equal to 1 to k, harmonic number into alternating harmonic number. Okay. This is an infinite Euler sum. So basically harmonic number into the cube of generalized harmonic number. This is again an infinite sum. We have harmonic number and multiple harmonic number. So as you can see here, for the finite case, we expressed the solution in terms of multiple harmonic number. For infinite sum, we are expressing the solution in terms of multiple zeta and multiple polylog. Okay, so to conclude, we saw that special functions provide the language of quantum field theory, and we introduced some new harmonic numbers such as alternating harmonic number, hyperharmonic number, and so on. And we saw that multiple zeta, multiple polylog, harmonic polylog, generalized polylog, they represent important classes of iterated sums and integrals. And we saw that two major computational routes for computing Feynman integrals are the differential equations method and Mellin-Barnett method. So all these special functions put together, they provide us with a symbolic framework for representing and computing some important classes of expressions arising in quantum field theory. Here are some references that you can look at for further reading. Okay, so that's all. Thank you very much for your attention.
Hello, I'm Aram Manasselyan from Mathematical Computations team at Wolfram, and today, together with my colleague Siria Sadettin, we will speak about the implementation of neural networks in Wolfram language for symbolic solutions of ordinary differential equations. Here is the outline of the talk. At first, I will speak about differential equation solvers in Wolfram language, dsolve and ndsolve. Next, I will discuss two interesting approaches from equations to solutions or from solutions to equations. After that, I will show how we can use neural networks in dsolve for symbolic solutions of ordinary differential equations, and will show some interesting examples. During second part of the talk, Siria will speak about how to train a neural network for differential equations, about training models, and training architectures. So let's start. As you possibly know, in Wolfram language there are two main functions for solving differential equations, dsolve and ndsolve. These two functions do the same job, but they are completely different in nature. ndsolve solves differential equations numerically, so its outcome is an interpolating function, as it is demonstrated here, and here is the plot. ndsolve is a very powerful function and can solve almost any differential equation, but it works only in some finite domains, and we have to provide enough number of initial or boundary conditions in order to get a solution. Also, all parameters in the equation must be numeric. In contrast to ndsolve, dsolve solves differential equations symbolically, so its outcome is an analytic expression. Here you can see the solution of the same equation obtained by dsolve, and again here is the plot. But for the case of dsolve, we can also have some symbolic parameters in the equation. For example, here a is a symbolic parameter, and the solution also depends on this parameter a. And here you can see the plot of the solution for various values of parameter a. Dissolve also can be used for differential equations without any initial and boundary conditions. In that case, dissolve returns the general solution of the equation, which contains some arbitrary constant coefficients, C1 in this case. So to summarize this part of the talk, I want to say that of course ndsolve is much more powerful than dissolve and can solve more differential equations, but the solutions obtained by dissolve are more general, easier to use, and easier to understand, and that is why we keep both functions in Wolfram language. So the next question is how to determine how powerful is dissolve. And we have two approaches to do that. The first approach can be called from equations to solutions. In this case, we generate a benchmark of few thousand ODEs taken from well-known textbooks and handbooks on differential equations such as Kamke, Polyanin-Zaitsev, Murphy, and many others. As a result, we will get a list of few thousand differential equations which in principle should have symbolic solutions because these are textbook examples. And we can try to solve all these examples using dissolve, and currently in version 15.0 the success rate is almost 94%, which is a really very good number and clearly indicates that all known solution methods available in the literature are already implemented inside dissolve. The second approach can be called from solutions to equations. In this case, we can generate millions of arbitrary functions containing some arbitrary combinations of elementary functions such as polynomials, trigonometric functions, inverse trigonometric functions, exponentials, logarithms, and others. And for each of these functions, we can generate its own differential equation for which the function will be a solution. As a result, we will get millions of differential equations together with their symbolic solutions. And again, we can try to solve these equations using dissolve. Of course, in this case, the success rate will be much lower because dissolve cannot solve arbitrary differential equations. But this approach allows us to get large data of differential equations together with their symbolic solutions. And we can use this data to train a neural network, and we can use this neural network to try to guess a solution for some other differential equations using machine learning algorithms. And here I want to announce that in version 15.0 we already have implemented a neural network-based solver for finding symbolic solutions of linear and nonlinear first-order differential equations. And this new solver can be called automatically inside dissolve only if dissolve fails to solve the equations or returns not good solutions. What I mean by not good solution? The implicit solutions or solutions containing unevaluated integrals or inverse functions or solutions with large leaf count. And here are few examples. In example 1, we have a linear first-order differential equation which contains only the derivative of dependent function f, so we can easily solve this equation by simple integration. But since the function to be integrated is quite complicated, the solution will have a large leaf count, as you can see here. But in version 15.0, dissolve returns a very nice and very simple solution for this equation using the new neural network method. And here is the plot of the solution, and we can easily verify that this solution is correct. In example 2, we have a nonlinear first-order differential equation for which dissolve returns really very bad solution in version 14.3. As you can see, it's an implicit solution. We have solve here, and also solution contains several unevaluated integrals. So this solution is almost unusable. But surprisingly, in version 15.0, dissolve returns a really very beautiful and simple solution for this complicated differential equation. And here is the plot of the solution. In example 3, we again have a nonlinear differential equation for which dsolve fails to return a solution. But again, in version 15.0, we have a beautiful solution provided by neural network methods. And finally, example 4 is a possible issue example. Here, again, we have a nonlinear first-order differential equation for which dsolve returns 4 branches of solutions in version 14.3. But as you can see here, in version 15.0, dsolve returns a much simpler solution, but only one branch. So if you are not happy with this solution because it is incomplete, you can use new dsolve option, method goes to classic, which will force dsolve not to call new neural network methods and will restore the old solution. That's all I have for today. So I will stop here to let Syria to continue with her part. Thank you very much.
Thank you, Adam. Hi, I'm Syria Sadedin from the machine learning team here at Wolfram, and I'm going to show you why training a neural network model is such a good alternative for solving ODEs that dsolve struggles with. Here's an overview of my presentation. We're going to start telling why training a model is a good alternative for solving ODEs, how we generate our synthetic data set with 1 million ODE solution pairs examples, how to go from the symbolic map to the tokenization form of the representation for the ODEs, what is our training pipeline to train the model, how we verify the outputs for dsolve, and what is the future of neural symbolic solvers. Let's start by understanding how the classical dsolve function works. Dsolve uses symbolic integration rules combined with pattern matching and sophisticated transformations heuristics. It's really good at what it was designed to do, but struggles with nonlinear ODEs that have complex compositions. More than that, there are equations that have clean solutions, but they don't match any of the known integration patterns. We did internal analysis on textbooks benchmarks and found that dsolve has about 6% failure rate on standard ODE problems. That might sound small, but when you are trying to solve a variety of equations, that gap becomes significant. So what is our alternative? Instead of relying on fixed rules, we train a neural network model. Rather than pattern matching against no integration techniques, it learns the deeper mathematical relationships. Here is a sample of generated pairs of problems and their solutions. Here you can see the complexity of the training problems and their solutions. Here is how we generate our synthetic dataset. We turn the problem upside down, from solution to equation, to automatically generate 1 million exact ODE solution pairs with no human labeling required. The core innovation here is that we needed no human labeling. Let me explain how we did this. First, we used the Wolfram Language symbolic engine to generate random elementary expressions for y. For example, something like x plus sin x plus c. Then, here is the key. We derive the ODE that this solution satisfies. We did this by taking the derivative of y and doing algebraic manipulation to obtain the differential equation. This process gives us pairs that are mathematically guaranteed to be correct. The result is 1 million pairs that are exact, diverse, and Wolfram language native. Here you can see some examples on how the problem and solution pairs look like. After generating our dataset, we needed to transform the human-readable problems into machine-readable problems. To achieve that, we converted the symbolic problems into its leaf representation. Look at the top of the slide. You see 4 simple examples that show what a leaf representation is. Let me walk through each one. Starting at the left, -2. This is as simple as it gets. The expression is just a number. In tree form, it's just a single leaf. For the second example, we have more structure. The square root operation has one child, the number 5. In the third example, times combine 2 things, the coefficient 42 and the power term. The power node takes the base x and the exponent 5. In the last example, -x is interpreted as -1 times x. In the tree form, x is a node, and the leaves are -1 and x. All mathematical expressions break down this way. The operations like plus or times, power, etc. form the internal nodes. The atoms like numbers, variables, or constants are leaves. To convert to tokens, we just walk through all the nodes and leaves in order, reading from left to right and bottom to top. Look at the dataset table on the slide. The problem prefix list and the solution prefix list show how we linearize the tree into a list. For the first solution, we have x plus c1, with the tree representation as follows. We have plus as the node and x and c1 as the leaves. Then we convert it into a list of tokens, reading from top to bottom and from left to right. Then we have plus x and c1. For the second solution example, we want to convert c1 plus sin of x into its leaf representation. We start with the operand plus, with arguments c1 and sin. And sin takes the argument x. Then we read from top to bottom and from left to right, writing plus, c1, sin, and finally x. Finally, we need to convert tokens into numbers. For that, we use the vocabulary predefined and the functions net encoder and net decoder from Wolfram Language. By using net encoder, we can convert the strings into numbers that represents the position of the string in the vocabulary. Now let's talk about how we train the model. Look at the architecture diagram on the left side of the slide. The model is an encoder-decoder transformer. On the encoder side, we have the input. On the decoder side, we have the output. The architecture is similar on both sides. On the left, the encoder takes your ODE as input tokens. It has multiple attention layers that learn relationships between the tokens. The encoder outputs a compressed understanding of the problem. On the right, the decoder takes the encoder outputs plus the previous solution tokens that have been generated so far. It also has multiple attention layers. At each step, it learns to predict what token should come next. The box in the middle zooms in the attention mechanism. This is the key part. For each token, the model asks, which other tokens matter for understanding this one? This is how the model learns mathematical relationships. Now, here is an important part of our strategy. We don't start by training on all 1 million examples. We train just 100 examples first. Because on a toy dataset, we can quickly answer crucial questions. Does the model learn? Does the model generalize? How fast does it train? Here is how we recreate the encoder-decoder transformer in Wolfram Language using NetGraph. After training this architecture using the netTrain function over our 100 examples, we can study the loss function for the training set and the validation set. We can see that both the orange line, which is the training loss, and the blue line, which is the validation loss, go down. That means the model is training. Once we validate that the approach works at this small scale, we scale up to 1 million examples. The architecture stays exactly the same. The only thing we change is more data. When we train on the full dataset, the model achieves 86% token level accuracy. There is something critical about how we integrate this into DSolve. Neural predictions are never trusted blindly. We must guarantee their correctness. The model performance is good, 86% accuracy on synthetic data, but we don't just return wherever the model predicts. Here is how it works in DSolve. First, the neural model proposes one or more candidate solutions for a given ODE. Second, each candidate is symbolically verified. We actually check whether it satisfies the differential equation using Wolfram Language symbolic verification. Third, only verified solutions are returned to the user. This is the key to making neural predictions trustworthy. Even if the model makes a mistake, we catch it before it reaches the user. Users always see mathematically correct symbolic solutions. There are no hallucinations, no unverified guesses. So what comes next? We are extending this approach in several directions. We are extending from first-order ODEs to second-order ODEs. And we want to apply this framework to the integrate function because integrate faces similar challenges to DSolve. It has a fixed library of rules that doesn't cover all the cases, and a neural symbolic approach can help here too. We want to assist, find sequence function, and many more. We want to use this framework not as a replacement for symbolic solvers, but as complements. Thank you for coming.
Hello everyone, my name is Oliver and I work in PD modeling, numerics, finite element method at Wolfram Research, and today I'm going to present a bit about what's new in PD modeling in version 15. All right, so let's start with the most important slide. If you're new to PD modeling, the way to find an introduction is to go to the PD models overview page. That is basically the introduction where you find all information about PD models that we have. So for example, acoustics, electromagnetics, fluid dynamics. You'll always find a guide page that collects all functionality that we have. There's going to be a monograph about the subject area. In some cases, we have verification tests that you can look at. We have models like application examples, large-scale application examples, and then there's some smaller application examples that we think are noteworthy, and you can just click on them and you'll get to the documentation section where they are presented. All right, so this is what you'd look at if you're getting started. If your specific application area is missing, that doesn't mean that we cannot solve it. It just means that we don't have a specific collection of material for that specific area. So not all cause is lost when it's not there. You just have to manually type the PDE then and solve it. So that's still possible. Okay, let's get into what's new in version 15. So we've introduced non-Cartesian coordinate charts into all PDE terms and the PDE components. So here's an example. So we have a diffusion PDE term, and we're specifying the coordinate chart goes to polar. So all coordinate charts that coordinate chart data supports are now supported in PDE terms and the components, and we'll see an example of this now. So here we compute an eigensystem of a Laplacian PDE term in the polar coordinate chart. We have a Dirichlet condition at the outer boundary and a periodic condition to map the sides. So now we solve this over a rectangle because it's a polar chart, but then we can use revolution plot to visualize the results. So this is a new functionality, and we'll see later an example where this comes in handy. In solid mechanics, there is great news. So we've added support for plasticity modeling, and there's an entire new monograph on plasticity. So it follows the same procedure. As always, there's an introductory example that shows what the problem is and how to address this without too much technical detail. And then we'll drill down into much more detail. So have a look at that if you're interested in that. There is a new function, equivalent strain, that basically does what von Mises stress does for stress. We do the same thing now for equivalent strain. So it finds a reduced strain, much similar to what von Mises stress does for the stress. There are spring and damper boundary conditions, and we're going to see an example of that. And there's additionally normal force and normal pressure specifications. That makes it a bit easier if you have normal forces, normal pressures. You could do that before, but now it's a bit simpler to do that. Okay, and all these are links. You can go to the documentation if you want to find more information. So plasticity. So I've just briefly shown you the monograph there. Plasticity means that if you deform a material beyond its yielding limit, it doesn't continue the usual strain stress curve of an elastic material, but at some point it just goes into elastoplastic deformation. So we'll have to detect this point and do something else along this line so that we get an elastoplastic behavior. We can do this, for example, for soil. So here you see some slope that has a pressure on top of it, and you'll see how the pressure distributes, and you can estimate from that whether the soil, whether this hang is going to collide or not. We can also do hysteresis. So when we have a yielding limit, we go to a maximum displacement, and when we unload this object, the return path can be different if we want to do that. So this is just a super quick overview of what's possible. You can have a look at the documentation for more details. The next thing I wanted to show are spring and damper boundary conditions. So in this example, I have a rectangle of a certain dimension. We have dependent variables u and v, independent x and y, Young's modulus, Poisson ratio, and thickness, and we use a plane stress formulation. We can generate the solid mechanics PD operator. I have a fixed condition on the left lower hand side. So that's where this rectangle, this beam is held fixed. And we have a load on the top in the middle. We'll see just the graphics just now. So here, so we solve this with ndsolve, the operator, the load, and the fixed constraint. And now we see we have held it fixed here. We put a pressure on this, and this is how this beam is deforming. Now, the new thing is that you can use solid boundary load value to specify a spring constant. And in this case, I said 10 kilonewtons per millimeters. And I've placed it on the left-hand part here. So that's where it's placed. And now we see that this spring is pressing back into the load, and the deformation then is, of course, different. Springs are used when you have a time-independent version. If you solve time-dependent solid mechanics problems, you can also use dampers, spring and dampers, and they work in a very similar way. You specify the damping constant to do that. Right. With this, you can model things like compression only or tension only boundary conditions. So a lot of new possibilities here in this area. Okay. For fluid flow, we've added new functionality, fluid viscosity. So when we look at the page for this, we'll see that you specify the variables, the parameters, and the velocity, and you get the viscosity out of it. So for a standard model where we have a dynamic viscosity, you get the dynamic viscosity back. So for Newtonian fluids, that's rather simple. But things become much more complicated when you have a non-Newtonian fluid. So in this case, we have a power law non-Newtonian model, and the fluid viscosity is much more complicated. So this is helpful when you want to compute fluid viscosity, especially for non-Newtonian fluids. Fluid stress, similar. Here you compute the viscous stress of a fluid. We've added new verification tests. There's a new non-Newtonian material model, Kasson-Papanagastu, that's been added. And we also added capabilities to compute swirling flow. And I'm going to show an example of that now. So swirling flow is related to axis symmetric flow. And in axis symmetric flow, you set that the derivative of the rotational independent variable theta is 0. And you do that by setting that the velocity in the rotational direction is 0. Swirling flow doesn't have this last assumption. It just says, so you can have a rotational velocity, but the derivative of that, of the rotational, of all components with regard to the rotational independent variable are set to 0. So here is an example. So the blue area represents a beaker, and the red grayish represents a mixer. So we have a 3-bladed mixer here that's put into this beaker. The first thing is we generate a mesh. And after that, we specify the variables and the parameters. So the variables here is u, v, and w. And in an axis symmetric flow, you'd set this component here to 0. But in this case, because we want to compute a swirling flow, it's non-zero. And we specify dynamic viscosity, mass density, and the coordinate chart is now cylindrical. And here is this coordinate chart that I've talked about initially. That's what triggered this whole coordinate chart introduction into the PD component. So now it's there, and we can now construct a fluid flow PD component that can model swirling flow. So what we do in the example now is we set a parametric boundary condition. So the u and v and w velocities are 0. The v velocity is has an angular velocity times the radius of the object. We specify a few additional boundary conditions, so basically a wall boundary condition, an axis of symmetry boundary condition. We specify what's happening at the top, and a reference pressure is also given. So now when we call parametric MD-solve, we have the operator, it's all set to 0, and the angular velocity now is the parameter. So we get a parametric function in the parameter of the angular velocity. And if I compute the solution for a specific angular velocity, so pi meters per second, we get the interpolating functions of the velocities and the pressure. And we can visualize this by using a function interpolation to compute the velocity magnitude of this. And this is the result of the velocity magnitude plot for velocity specified as pi meters per second. Okay, so you can, because it's a parametric function now, you can do this interactively also. So here we show various solution for various rotational velocities, and we'll see how the fluid flow, the velocity magnitude changes depending on the fluid flow velocity in the rotational direction. Okay. We've added a few new application examples. So if you are new to PD modeling, there is an introduction to PD modeling where we show how we develop application examples. And we'll start by using a very simple model and then drill deeper and deeper. And we also show that where we went wrong and decided how to do things differently too, so that you can follow the creation of these application models. The idea is to help you understand how these are developed and to develop a feeling for how to generate or how to create complicated PDE modeling application examples. And again, you just follow the link here and you'll get to the reference page in the documentation. For the physics inclined people, we've added, and quantum mechanics inclined people, we've added a Schrödinger-Poisson, a Schrödinger-Newton application example. We have a new application example in conjunction with System Modeler, where we do the cooling of a room with an HVAC. That's a combined finite element system modeler model. The spine surgery rod and the slope stability application examples showcase the plastic deformation functionality that we have. Biomechanics of human tendon has been updated, and there is a new 3D printing and mechanical design application example that shows how you can use 3D printing and access the stability of the object that you've created. So again, have a look at these if these are of interest for you. There are a few other changes I'd like to mention. So in heat transfer, we've added thickness and cross-sectional area parameters, and these make it easier to do models in 2D and 1D. So that's hopefully useful. In electromagnetics, we added post-processing functions to compute the electromagnetic, the magnetic flux density and the magnetic field intensity, H and B field respectively, and both work with scalar and vector potentials. And the last thing I want to mention is that for linear solve, we've added a new method, a new linear solver that's MUMS. And in version 15, MUMS is the default finite element software of finite element solver on ARM hardware. And the reason is that especially Mac and that switch to ARM, you'd often had to switch to Rosetta to be able to solve highly nonlinear problems, because the previously default solver was Paradiso, which is an Intel MKL provided solver that wasn't available on ARM hardware directly. You'd have to use Rosetta to do that, but now this problem should be solved, and it should be completely transparent to you, so you shouldn't even be aware of that. Yeah. Okay, that's about what's new in PDE modeling. Thanks for your attention. I do like to point out that we try to do a yearly PDE finite element conference. We don't have a date for the upcoming conference yet, but watch out for that. And I hope to see you there.
Thank you very much, Oliver. And maybe the other presenters can also mic up or even join by camera if that's possible. So please go ahead and join if you can. So it's been a great pleasure to do all this, but it's time for a bit of discussion. So go ahead if the other presenters want to at least mic up and try and participate in some of the remaining discussion. Okay, so I'm going to go ahead and share the usual notebook as well. Okay, so thank you all for being so patient sitting through all these talks. It's a lot of work to not just to prepare talks, but also listen to them. So I think in the few minutes remaining, I should just say that there was one question which, from a couple of people about them not being able to run the example. If that's an issue, just please contact support. It could be you just need to restart your system because sometimes a download to take place, something of that sort. Do try it out. If there's a deeper issue, let us know. Aside from that, maybe if the other presenters want to say a few things, let's just begin. Adam, can you? Yeah, go ahead.
Okay. Yeah. So we have added the new features for non-commutative algebras in version 15, and so there were some questions about applications. So the documentation pages for non-commutative algebra have some applications of course these are just very simple applications. I'm sure there are quite many more advanced applications, as I've seen in the questions. There are, in physics specifically, there are many possible applications for this. Other than that, we also have a tutorial on non-commutative algebra that gives some more specifics about the implementations and about the possible non-commutative algebras that could be implemented and used. So you can look at the tutorial also. So
great.
That's about it.
Thank you, Adam. I think this is a kind of phenomenal piece of work. It didn't exist 1 year ago. Now it's all kind of done. It is somewhat technical, but then there's also a big audience for it. So I'm sure they'll be happy to see it in the system. We'll just go and sequence, and let's look at maybe if Jayanta has any thoughts on behalf of himself and Tigran. Jayant, any thoughts about where you think things might go from here on for these quantum field theory related developments? Anything interesting you want to mention?
Well, I think there are several existing packages for doing Feynman integral calculations like FindCalc, Polylog tools, and so on. And I just want to say that we have derived a lot of inspirations from those. And of course, we would like to support many other basic functionalities related to such calculations, if not very advanced things. So there is a lot more work to do in such areas. And also one thing to notice is that this is still a research field. So it is hard to say like which kind of special functions or which kind of computations would actually be helpful in the future. So that is another judgment that we have to make usually.
Yeah.
But I think for now we have laid down the foundation, at least in Wolfram language, for doing these calculations. There will be a blog post sometime soon where we will have more details and so on about these. So yeah, hopefully there will be some more functionalities in the future.
Yeah, that's great. And what the point Jayanta made about specialized package, we are in no way close to providing the functionality of FindCalc or any of these wonderful packages. Although we know the individual people quite well, I think they serve a different purpose. They are at a different level of complexity. I don't think we can even dream of doing that. But what we'd like to do is to give our own users a flavor of what's possible for particle physics using Mathematica. Tigran, if you have just a minute, thank you, Jayanta. So Tigran, if you just maybe half a minute, any quick comment about your recent trip to the SIAM where you presented a talk on special learning, like one two sentences of like a message that you think you received about Wolfram language and special functions from there.
Oh yeah, so I will say a simple words that math research is going on, math development are going on, and AI is somehow affecting all this stuff, but we are doing our job, and a lot of new functionality is coming, in fact.
Great. Now, I get the impression that people are still very positive about both the traditional and the AI-based approaches. So,
sure.
Mathematics is in good health. Nothing to fear.
Yeah.
Thank you, Tigran.
AI is helping to resolve some problems that were very hard to solve, in fact.
Sure. Thank you. So, Aram, how do you feel about this first, I would say, successful neural network, very successful neural network project? How did it fit well into DSolve, or do you think there was some serious issues that you struggled with? How did it go?
Yeah, actually, this neural network project was quite interesting, experimental project for us, and surprisingly, it gave really very nice result. We get some very beautiful solutions for quite complicated nonlinear differential equations. And I think we will continue in this direction to go for some other types of ordinary differential equations. For example, we can try higher order differential equations, which also can be quite useful for this neural network project.
Of course, thank you. Yeah, I agree with you completely, Aram. And Surya, as a kind of outsider to mathematical computation, how do you feel? Do you feel comfortable working on this kind of combination of very classical mathematics and very modern, different? You've done a great job, I should say, but how do you feel about it yourself? Do you feel you want to go on working, or are you a little tired of it? What's your thought?
Well, I have to say I feel comfortable and I am happy to apply ground science into technology because like my background is physics and I'm happy to have the opportunity to work with technology and apply what I learned before. So I
Great.
think this is nice for me.
Wonderful. Okay, thank you. And Oliver, I should just say that Aram mentioned that ND-Sol works on a finite interval, but maybe in some far galaxy, very far away, Oliver already has implemented a version which does work on infinite intervals. So Oliver is always doing nice things. So Oliver, how has it gone? How has version 15 gone for you? Just a minute, because
Yeah, so 15 was fairly big release for us. Specifically, the plasticity was quite complicated to get to work, but we got there, so that's good. And now I think going forward, there is a little bit of a backlog of wishes that Stephen has. So we'll have to look at those a bit and try to implement some of those requests.
yes.
And one thing I'd like to encourage everyone to, so if you're working on PD or finite element models and run into trouble, please don't hesitate to contact us. I mean, for us, this is a bit a way to assess what type of functionality people use, where we should put our focus, what we should improve, extend upon or some, and things like that. So if you want to talk PDEs and finite element, contact me. I enjoy that.
Yeah, Oliver's fantastic on communication. So I think that I totally agree that he's the right person to talk. Okay, so then maybe I think I really should hand back to Jamie and Robs to wrap the webinar. But it's a great pleasure to have you all here. And I'll stop. Thank you all for all the attention you gave us today.
Thanks, Devendra. Thanks to all our presenters. I'll just put my browser page here back on the page to share with you. So here's another section of Stephen's blog where more information can be devoured regarding these topics. So I do encourage you to check out that blog. We'll send a link to you in your follow-up email that has, we'll also have a link to the recording today. But just a reminder that our final webinar in the series takes place next week on Thursday. We hope you'll join us. We'll be talking about everything notebooks, notebook technology, and also the latest AI assistant with Ellen Joyce and John Foltz. And Ellen will also be giving a demo about the latest for external coding environment with MCP connectors. So this will be of interest to many people, I'm sure. So thanks to everyone for all their efforts in responding to questions and for you for your attention.